So yeah, my name's Dave O'Leary. I'm recently finished a PhD in the University of Galway, and it's not related to this at all whatsoever. It's a completely different subject, still using geophysics, but not in caves. So this was a little side project that came up sort of during the PhD because of what I do in terms of geophysics. And Eamon and Colin and a few other people from the Geopark who were interested in a particular cave in the Burren said, can you help us out in finding something about this cave, which I'll go into more. And so that's where I stood in and said I'd help out. So I'm going to explain a little bit about what geophysics is, first of all, because it might not be familiar to everyone here, and then about what caves are and how caves are in the Burren and how we can sort of marry the two together. And a little bit about myself as well, because everyone may know Eamon, but they don't know me. So yeah, I did my undergrad in 2005 and 2009 in Galway. Then went and did a master's, and I actually worked in the oil and gas industry then for about 8 years after that, using this geophysics to help in that, or to work in that industry. And then I came back to do a PhD and research, which I'm currently doing now, again, on something completely different. So my own research topic is about soils and making maps of soils using geophysics, using satellites, using aeroplanes and stuff like that. So completely different to what is today, but still using this geophysics term. But just in the oil and gas industry, I said I'd touch on it a quick bit just to give a bit of background to myself. What I used to do was make these images of under the ground using these things, which are called air guns. They set off a little air bubble explosion in the water, and it bounces off and echoes off all the rock layers underneath the ground. And just like shouting at a cliff and hearing your voice come back, you can tell then how far down those rock layers are. And when you do that explosions or those sources from enough places and enough different directions, you can build up an image, almost like an X-ray or an MRI scanner. I used to live and work on that ship on the right-hand side, so that's a picture of it. I used to just sit and receive the data up onto it. But my favorite part about working and living offshore, of course, was all the extra stuff. So I got to drive boats and fly in helicopters and travel all over the world. So I think my background in earth and ocean sciences from Galway really got me into that. And of course, traveling and working and living all over the world meant I got to do lots of travel. So that's Everest Base Camp. I was very lucky to get to go to Everest. I went on a motorbike trip in the Himalayas where every photo we took, I swear it looked like a boy band. There's nothing I could do about it. Every single one. Weddings in India and just lots of travel and stuff. So that was just sort of a little bit of background on me and myself. So yeah, where I am now is doing this research with Galway and Teagasc. It's about mapping peat and organic soils in Ireland in general and sort of figuring out how we're going to manage these in the future. But I said I'd start this talk more so by talking about what geophysics is, because that's something that, again, not everyone's really familiar with. So this is an image I stole from the USGS, US Geological Society, and I think it really nicely explains what geophysics is. So geophysics, what we're trying to do with geophysics is figure out what's going on under the ground, but without going underground, if that makes sense. So it sort of appears like this. We make these images and interpretations about what's happening under the ground, but in reality, of course, it's a lot more, I won't say complicated, more complex, let's say. We have expensive equipment. We use complicated maths and physics to try and figure out what's going on. We're sort of trying to marry the physics of the world, so things like electromagnetic induction or gravity or magnetics, into how they're affected by what's happening under the ground. And we're trying to look for anomalies or changes of how that signal is changing. We can do it a number of ways. We can send a signal into the ground, and that's the bit of equipment I have over there, which I can talk about later on. So we actually send something into the ground and we measure how it returns to us. Or we can measure something that's just there naturally, like say the force of gravity or magnetics or something like this. And by measuring that and measuring changes in that as you move through space, it can tell you about what's happening under the ground. So caves then. So these are just some images of caves, not necessarily from the Burren, but they're representative of caves. This is taken from, from Bermuda. It's just a nice picture of a cave. And then this is sort of the problem that we have and how geophysics can be used. So, on the surface, of course, you can't see caves. You're just walking across the surface and you really don't know what's underneath the ground, but it could be very, very complex. We have air-filled caves, water-filled caves. They could be filled with sediment. They could be very complex geometrically, as in like they have weird shapes. They can be filled with air or water. They're just basically openings in the rock. And that's actually something we can exploit with geophysics. Because it's an opening in the rock, it's different from the rock around it. So if rock is very dense, an air-filled cave is obviously not very dense. Or if a rock is if it has a lot of water or fluid in it, it can conduct electricity very well, whereas air can't conduct electricity. So we can use these different properties of the subsurface to try and figure out or try and map or use geophysics to find where these anomalies happen. And I said I'd touch on a few different methods. So the first one, I touched on it already, is gravity. So gravity is all around us now. It's what's keeping us stuck to the ground. It's what's keeping everything, what is down is because gravity is pointing in a certain direction. But what you may not know is that as you walk over the ground, the force of gravity changes ever so slightly, very, very minuscule amounts. And that is driven by the density of what's under the ground. So if you have an air-filled cave that's less dense, you'll have slightly less gravity over that cave than you will over solid rock. And we can exploit that. So I just have a little animation of a guy walking across the ground, and as he gets across the air-filled cavity, you get a slight decrease in gravity. And then we can use that. So this is, it's a very complex measurement to take. You put an instrument on the ground, and it has to be perfectly level, and there can be no wind shaking it. It's basically measured by a very sensitive spring. So as the force of gravity increases, the spring extends slightly, and as the gravity decreases, it contracts slightly. But it's very, very minuscule. You have to account for things like if you're in a valley, the mountains beside you actually affect the gravity of where you're standing as well. So it's quite complex. You have to know your topography. You have to know where you are in terms of north or south, because the further north or south you are from the equator, gravity is slightly different as well. You have to know where the moon and sun are, because the moon and sun, of course, cause the tides, which is a pulling of gravity as well. So all of these different things are taken into account. So it's a simplified view here, but gravity can be used to map things. This is a 2D line. So when I say 2D, I mean we walk across the ground and we're getting a single profile. But it can be done in 3 dimensions as well, and can be done from aeroplanes. And this is just an example taken from, I think, a cave in Croatia, where they've flown a gravity survey over the top, and they've been able to map out where the cave is using gravity. So again, just a technique that can be used to help find caves necessarily on the surface. The second method I'm talking about is called electrical resistivity. So again, I sort of touched on this. This is when you send an electrical signal into the ground, and you measure how resistive the ground is to that electrical current. It's quite a simple operation compared to the gravity. You have 4 electrodes which are stuck into the ground. 2 of them have a current running between them, and then you measure the voltage on the other 2. So it's just like putting a voltmeter onto your battery and seeing what the voltage is. Different rocks and different sediments in the ground have different electrical conductive properties. If they're clay, for example, they're quite conductive. If they're filled with water, they're quite conductive. If you have an air-filled cave, it's infinitely resistive. In fact, it completely resists signal, so you're not going to get much signal passing through a cave. And how these are set up, so these are arranged, A, M, N, B, how far apart they are and how they're arranged in terms of which ones are conducting current and which ones are measuring, you can get different depths on how deep you're going to measure. And I have a little, of course, I love my animation, so I have a little animation as well. So I have this bit of kit with us here, and we can talk about it more during the break. But effectively, you can set up a kit, you can lay it out along a straight line and put all these electrodes into the ground and then measure what happens under the ground, and it's sort of like this. So you can see as the red ones are putting current into the ground and the blue ones are measuring, and the further apart they are, the deeper you see, basically. And you build up this little sort of triangular profile under the ground of how resistive the ground is. If you then have a model of the Earth, just like the last one, where we have 2 air-filled cavities and we have rock all around it, and as you can see, when it's measuring in where the air is, it's going to get very high resistivity. And if we then take an output, or what this may look like, you can see that we have air-filled cavities, areas that are very, very highly resistive. So again, I think quite simple conceptualization of what it is we're doing. Now, when Eamon asked me to come down and give the talk, I tried to do a bit of research into what's been done in the Burren using geophysics in caves and sort of this whole area before. And funnily enough, I realized myself during my undergrad, that's my undergrad thesis, and it's titled The Detection of Cavities in Karst Limestone Using Gravity and Electrical Resistivity. So literally everything we just talked about, I actually did during my undergrad before I even knew that this talk was ever going to happen. And I said I'd talk a little bit about it today as well, because it uses those 2. So this is just north, that's Gort, just there. So this is just north of Gort, just in Cool. It's a cave called the Kiltartan Cave, or Pula, I can't remember the other name for it. There's another name for it as well, but I knew it as Kiltartan Cave when I was doing this work. And my undergrad thesis was to go out and just try and find where these caves were. Now, we knew there was been a lot of people do caving, and these maps had been made by cavers who've been down into the caves before. So this is a little access road that we could drive along. This is a farmer's field just here, and there's a wall along the top here. And there was basically a tree just sitting there where the entrance is, where people had climbed down into the cave. And they'd gone down and drawn maps and taken measurements and sort of, roughed out where they thought the cave was relative to the surface. And then I went and I did these 3 lines, and I'll show each of them in a second. So line 1, line 2, and line 3. And we did just what I talked about, the gravity and the electrical resistivity. So in the gravity, you can see where there's dips in the gravity, And where there's high resistivities, we've been able to interpret cave systems, and that is line 1, so across here. So this is the main cave system that we picked up. And then possibly a second cave system somewhere around here using those 2 methods. Line 2, which is this one here. So starting at this end and going to this end, left to right. Again, lows in gravity, high electrical resistivity, and we've been able to interpret these caves leading into this area at the end. And line 3, which is this one here, which actually crossed into a neighboring field, so we could only run the electrical resistivity part from this part. But again, we're picking up some sort of cave, possibly at the start, and then another maybe unmapped cave before. So these are ways that from the surface we've been able to find where caves are. And this is way back in 2008, again, before sort of my intro to geophysics. So that's all on top of the caves, which is really nice. But what about inside the caves? And this is the problem that Eamon and Colin and a few other people in Galway came to us with as geophysicists and said, how can we help inside a cave? Which is something that hadn't really been done before, I wouldn't say around the world because it's been used for mining applications, but in terms of a research question of what could we do geophysics in a cave, or what could we find? This is one of the first times I'd heard of it, so I was really excited to get in and give it a go. So this cave is called Vigo Cave or Vigo Cave. I never know which way it's supposed to be pronounced. We'll go with Vigo. It's just close to Currafin. I have a map showing where it is now in a second. And the question was, there's sediments in this cave, and I have a few videos and images which will show it, but how deep are those sediments? So, these sediments are in place. They're a bit different for a number of reasons. But how deep were the sediments? That was the question that I was asked to help with. So, Vigo Cave. So that's Currafin. We're not 2 million miles away from where we are now. That's Vigo Cave here, where it is in Ireland. This is a drone image that I took up and just took a picture of it looking that way back into it. So the entrance to the cave is just located close to the forest, and it goes into the back of the hill. Clifton Hill, I think is the name. And that's just the same image looking up out of the entrance of the cave, back towards where the drone image was taken from. I'm not a geologist in any way, shape, or form, but I do have a few of these images thrown in just to give context of where it's sitting. So Eamon mentioned about the sandstones and the shales and then the limestone. So it's pretty much sitting on the boundary between the two. We have sandstones and shales on top, at the roof of the cave, and then it's in the limestone section beneath. And these are just some possible cross sections. Thanks to Colin for providing them to give a bit of context of where we're sitting in the geology of the cave, of the burn. Just like the Kiltartan Cave, cavers have been down into this for many years and have done lots of different surveys to try and figure out exactly the size and shape and how it all looks. So this is just the caver's representation of the cave, from the entrance sloping down and then going through the different cave. There's different geometries. And this is a nice 3D representation, which I'll show a bit more of as well, because that was the whole thing. We're bringing these old caves into the modern realm using 3D images and geophysics. So it's a little bit different from caves in the Burren in general. We're all familiar with the likes of Allowee Cave or the Doolin Cave. This is higher, as I understand it, in the topography. So it's quite high in elevation. It's sort of separated from the normal hydrology of the Burren. So it's not part of, it has no running water through it at the moment, for example. It has a sloped entrance, which as far as I understand it is quite unique for the Burren as well. And it's assumed to be very old as well, even compared to other caves. So that's what makes it sort of unique. And because it's so old and because it's now separated from the hydrology, and because it's filled with sediments, the age of those sediments and where those sediments came from is an important question, because it can tell us about Ireland's past that may have been lost. If sediments are trapped in this cave and they're sediments that aren't currently been, they're not activated, they're not part of the current hydrology, they must have been there for quite a while. And it means that those same sediments that may have been on the surface at some point have been wiped away, but they're still present here. So it's a part of Ireland's history that is missing on the surface landscape, but it may be held and preserved inside this cave. So knowing how deep these sediments were, knowing how far we may have to core down into it, knowing if there's particular areas of interest, that's where the geophysics can help. So could we come into this cave and get a sort of a base? Where's the bottom of the cave actually, not where the sediment bottom is now. So a current interpretation of the cave, this is again from Colin's work. So at the entrance area, coarse gravel, angular sandstone blocks, large limestone till, and some maybe recent collapse features, relatively recent. In the middle section of the cave, some clay units. There's, again, I'm not a geologist or a sedimentologist, so this is just more of for context about what's there at the moment. And then at the far end, it's more various sediments as well. And again, Colin is here, so he can probably answer more questions on the actual sediments about it. But this is just where we are at the moment, context-wise. So the plan was, can we go into this cave and do this geophysical survey? So can we bring the ERT equipment down in? We bring it down into the cave, set it up, and try and acquire some electrical resistivity measurements. Now, I'll throw some caveats in straight away. All the examples I showed before, everything was along a flat surface. As soon as you introduce this topography, or this like changing surface, it complicates everything, of course, because now the electrodes are no longer sort of facing straight down. They're putting signal in at angles. So it gets quite confusing and complex. That's just one thing. Another thing is now they're in a cave, which has walls on either side, which are hard rock. And we don't know if they go straight down or we don't know if they get wider. The electrical signal isn't a perfectly straight line. It spreads out like a bubble into the ground. So if that electrical signal is interfacing with the rock, it's going to affect how that electrical signal is returned to us as well. So we may be just measuring the walls of the cave as opposed to the sediments directly. So a few just caveats. We're working in a 3D environment here, whereas usually when you're in a field in the middle of wherever, you kind of expect laterally that the electrical signal won't change. So that's a 2D environment, a 2D representation is fine. But in the cave, we have to think about 3D. So these are just some images of the cave with the equipment that I have over there, so you can sort of get a feeling for what it was like down there. First of all, and you can pick up the bit of a kit, it's not easy to bring it down into the cave, and Eamon and Colin were there with us on the day bringing it down. It was a full day's operation, and it was 25 degrees in the air, but luckily the cave was nice and cool, so it wasn't so bad. It's also quite steep sloping down, so again, moving this equipment in and out of the cave was difficult and fun. And it's quite tight. Like, I'm about 6 foot tall. I was crouching for a lot of the places inside this cave as well. And I do have a little video, which I hope will work, just to show you what that was like. Yeah. So, again, this is just me walking with a head torch with that bit of kit for us to set up in the center of the cave. I'm walking deeper into the cave now, so we're moving towards the back. It's quite tight. I definitely couldn't touch the walls either side, and a lot of times crouching to get down through it as well. Hence the shaky Blair Witch style camera work. Another issue with the equipment is it's a good bit of kit, but the distance between where we can put these little electrodes into the ground maximum is 10 meters. So we have 10 meters of cable to try and wind around and push and not step on and not fall over and trip. I think it's coming up in a second now, so there's a hole in the ground where Colin has done some work digging as well, which we have to work around. The topography was quite rough, so like trying to get these electrodes into the ground could have been difficult. It was pitch black, of course. You're in a cave 100 meters deep underneath a hill. There, this is a little, so Colin has dug some work there to try and see what sediments were already present in the cave, but again, knowing how deep to dig is what we were there for. And yeah, so that's it. So, where is that gone? Lovely. So, now I talked about the whole 2D problem. So this is the results, right? This is quite similar to what we saw before in terms of like results. So you have something that looks like very high resistivity and then low resistivity. And this, this might seem reasonable, right? You might look at this and say this is a good result because of what we talked about earlier. But I mentioned the fact that we're in, first of all, high topography, and we're also in this 3D environment where we don't know about the walls of the cave or how steep they are, if they're straight down, if they're getting wider. So although this looks like a reasonable result, this was done using a 2D software, a bit of mathematics that involves only the 2D. It only thinks about a straight line straight down into this cave. But as I said, the electrical signal, it sort of spreads out like a bubble. So when you put the current into the ground, although it's mostly focused between the two electrodes, it spreads out. And because it spreads out, it's sort of sampling the rock walls around it. And what threw me, how I knew this was wrong straight away is that it's perfectly following the topography, right? It's going up when the topography is going up, and it's going down when the topography is going down. So all that tells me is that the signal is just following this sort of where we are on the surface. It's not actually telling you anything really about how deep the sediments are. So we have to start thinking in 3D, and this is where we're sort of bringing these possibly million-year-old caves into the sort of modern world. So before I'd done any work on this, and this sort of nice colorful image on the top is part of what that was. Colin and a company from the north, I think, they'd done this thing called a laser scan survey. So a laser scan is where they put this bit of equipment into the cave and it fires out lasers, and it's able to tell them once it knows where it is and it knows how far the lasers have gone and bounced back, it's able to build this 3D image of the inside of the cave or where I was walking there, where the video was. And so this is just that. So this is the air-filled part of the cave in 3D using the laser scan data. So, it's very complex. We saw that from the video. It's up and down, it's all over the place, but we have this 3D representation. So when you have a 3D representation of something, you can build a 3D world. So this is taking a DEM and putting the cave into this now 3D modeled environment. We can see how the cave sits in the environment and where it sits under the ground. which I thought was really cool when I was doing that. And I'm able to build these little videos. So that's really nice. And of course, I don't think any 3D environment would be complete without what's called a fly-through, where we actually go down into the cave in 3D. We can bring everyone down on the day and see what it looked like. And this is, it's not a million miles away from what it looks like on the day. It's very, very cool. And you can see a lot better than I did with the video. So you can see that. And in terms of heights, that is probably about 1.5 meters or maybe 2 meters max in some places and down into the mouth. So this is really cool. It looks really nice. It's nice for presentations, right? But as it stands, there's no data, right? All we have is this air-filled cave in an empty 3D virtual world with nothing filling the gaps underneath the ground. Like when I say under the ground, I mean all this air that looks like air, that's all rock, obviously, right? That's not air underneath the ground, that's rock. So we have to fill that with something. And what we're going to fill it with is that geophysical data that we acquired. So we went out and we spent the day collecting the data all along where you can see here. And then this is the result. So we're now able to fill that world with data. Now, I will throw a few caveats in as well, of course. When we have this single 2D line, we have the single sort of line of data going through the middle of a cave. So that's it. That's all we have to fill this entire under the ground with. But so basically, as a caveat, what I'll say is the further away you go from that cave, the worse the data is. So I wouldn't necessarily trust it once it goes beyond a certain distance, but it's a representation. If we look at it just without it moving around and throwing my eyes off. So this is just looking along the cave. So this is just a slice that I took through the cave. And then this is a slice perpendicular to where the cave is going. So, once you go below a certain distance, I wouldn't really trust the data. And we have metrics to say how far away, we can believe. But even taking this now, we have some sediments. We have this anomaly in the middle, which is the new thing, which is what we're hoping to go sample at some point. And then we have the cave mouth. And again, the data on either end, I wouldn't really trust either. But we have now a representation in 3D of how deep the sediments might be underneath the cave. So we can go out and start taking some cores. We can go out with some more samples and be more focused. And particularly this area here, which is not known. This is a low in the resistivity, which is matching the resistivity of the sediments, which means it's possibly a collapse feature or maybe a new vertical intrusion that wasn't known about before. So it's just, again, something to point at. That's the idea, right? Now at least we know something more about the cave than we did before. So I'm glad Eamon went a bit over time because I'm a bit under time, so it all lines up. That's it. That's geophysics. That's trying to bring these caves into the 21st century in some way by using modern data. Thank you.